Choosing between PBr3 and Tosyl chloride. Both PBr3 and Tosyl chloride change OH into a good leaving group. The main difference between the two is PBr3 changes an OH into a bromide by an SN2 reaction. Since it's an SN2 reaction, the stereochemistry of the alpha carbon is inverted. Tosyl chloride, on the other hand, will change an OH into a tosylate leaving group, and the stereocenter remains the same because the carbon-oxygen bond does not change. Where this can come in useful. Say you start off with a single enantiomerically pure optically active alcohol, so like this alcohol, and you want to make either of these two nitriles. Well, the nitriles are made by an SN2 reaction. And since it's an SN2 reaction, this nitrile is going to invert your leaving group. I'm going to use Lg in parentheses for the top one. This bottom one, since this is a dash, means it has to come from a wedge, Lg. Now, when we compare our alcohol, this alcohol is a dash, that leaving group is a dash, so the configuration did not change. And so for the top case, we would use Tosyl chloride. For the bottom case, where we actually inverted to give the leaving group as a wedge, we would use PBr3. And so now we can go back and change the leaving group to the appropriate one. The top case becomes an OTS. The bottom case becomes a Br, and there's our complete synthesis, giving us either of these two nitriles in their optically active forms. This can also come in handy when making one of two diastereomers of an alkene. Keep in mind that alkenes can be made from an E2 reaction. If you're looking for only one of two diastereomers, you can use the anti-coplanar characteristics of an E2. Take advantage of this. Your leaving group and your hydrogen have to be anti-coplanar to each other. This methyl group and this ethyl group are both on the same side, so we'll call them both wedges. This methyl group and this methyl group are anti to each other, so if this methyl group is a wedge, this methyl group also would be a wedge. So either this diastereomer or it's an enantiomer where we switch the wedges for dashes. Is necessary to make this diastereomer of the alkene. And the way you can use the anti-coplanar rule is if you have both of these, both your alpha carbon and your beta carbon are both chiral. That's when you can take full advantage of it. To make this diastereomer here, we simply use the other diastereomer up above. Leaving group, hydrogen. This methyl and this methyl are cis to each other, and so they both are wedges, and the ethyl group becomes a dash. Or we can use its enantiomer. leaving groups here, methyl group's a dash, methyl group's a dash, and then the ethyl group is a wedge. So either of these two. And that nice part about this is if we use this optically active alcohol, we can generate either of these two situations using Tosyl chloride or PBr3. First thing we need to do is redraw this. So the OH group and the H we're planning on taking off are anticoplanar to this, to each other. So when the OH becomes a line, this methyl group becomes a wedge. When this hydrogen, which was a dash, goes to where this methyl group is, this methyl group becomes a wedge, goes to where the ethyl group was, and the ethyl group becomes a dash here. You can double check this by checking out the stereochemistry. In this case, this is an S stereocenter. And when we double check, this is still an S. This situation, as written, is the same. If we label these over here as A, B, C, D, this is the same as structure C. And so by this configuration, we would expect to see C if we did an E2 reaction. So, in order to do an E2, we have to convert this into a good leaving group, which we use Tosyl chloride. OTS. Hydrogen. And then, upon the application of a base, such as sodium methoxide, we get this diastereomer. To get the other diastereomer, we have to invert this OH group. So we use PBr3. And when we do so, we keep the less stereocenter on the left the same because in an SN2 reaction only inverts the alpha carbon. So, this Br becomes a dash. This is situation B over here. Again, we add our base, sodium methoxide, to that, and we get our alkene. Now, these optically active alcohols are easy to come by. Main way we can make them is if we start off with an optically active epoxide plus a Grignard, presence of ether followed by H3O plus, gives us our optically active alcohols, which then we can use in any of these reactions to generate either diastereomer of alkene or any nitrile or other product of an SN2 reaction.